Okay, we will start with this session. So in this session, we will conduct a virtual experiment. That is your experiment number 4 from your syllabus. So this experiment, it is based on the force vibration. That is the module number 5. So aim of the experiment is to study the vibration response of a system. So the system will be a vibratory system. And for that vibratory system, we have to measure the response. So here response is nothing but the displacement. So basically, aim of the experiment is to measure the displacement. So I will write here x, or we will measure this displacement or response in terms of the amplitude. So generally we take this value as a capital A. Okay. So we will measure this in terms of millimeter, or we can measure in terms of meter. So when we measure the response of a vibratory system, it depends on the frequency of the excitation. So this frequency is represented by omega. So if we change the value of omega from 0 to some finite value, then depending on this omega, that is the frequency of excitation, your displacement or this amplitude A, it will change. So we have to observe how this amplitude is varying with respect to the external frequency. Okay, and at which point we get the maximum value of this amplitude A. So we have to find out that value, and from this we have to predict what is the resonance condition. Okay, so we have studied what is meaning of resonance. Okay, so resonance is the condition where the system's natural frequency omega n, it matches with the frequency of the excitation. That is called as a forcing frequency or external frequency. For this condition, it is called as a resonance. Okay, and at resonance, system will oscillate with the maximum amplitude. So when we design any system, then we generally avoid this condition where the system's frequency, that is a natural frequency, becomes equal to the external, that is a resonance frequency. Okay, so if we allow the system to oscillate with this frequency, omega is equal to omega n, then there is possibility that the mass of the system will oscillate with the maximum amplitude and it will become uncontrollable. Okay, so it may cause the damage to the system. So in order to avoid that damage and for the smooth running of that mechanism or that system, we need to avoid this condition. Okay, so when we design any system, any vibratory system, then we need to perform one experiment where we can study the response at the various values of omega. So omega, it will vary from 0 to some finite value. So this finite value, it is nothing but the operating range. So this will be the operating range. And within this operating range, we need to observe what is the response of that system. Okay, so this is the aim of this experiment. We want to study the response of the system for the various values of the omega. Okay, so for the write up, you just write down this aim. Okay, then I will draw the experiment diagram. So this is the system. So we have taken a schematic system, okay, which carries one mass, and this mass is supported on this spring and damper. Okay, so we can assume this is the model of a vibratory platform. Okay, so maybe in the force vibration, I have shown what is a vibratory platform or vibratory conveyor. So generally, a vibratory conveyor consists of a platform, so which is generally used for the material sorting. So this is the vibratory platform. Okay, it is supported on these springs. Like this. Okay, and for the force vibration, that means in order to provide the external frequency, we connect the motor having the eccentric mass. So suppose this is the motor which is connected to this platform. Okay, and this motor, it carries some eccentric mass. So when it rotates, it will create some centrifugal force. So this value is nothing but F0, which is equal to m0r omega square. So m0 is the mass of the this eccentric mass. Okay, then r is the eccentricity, that is the radius of this mass, and omega, it is the speed. So this is called as a exciting force. So because of this exciting force F0, this system will oscillate. F is equal to F0 sine omega t. Okay, so this is the schematic model for this system. So this is a physical system, that is a vibratory conveyor. And this is the equivalent model, that is a vibration model. Now for the oscillation, we will connect a motor to this mass. So this motor, it is having one eccentric mass. So this is the shaft. Now this motor is connected on this mass. And this is the eccentric mass, which is called as a m0. Okay, this capital M, it is the mass of the platform. So this is the m0 is the eccentric mass, and for the motor, the mass is taken as a m. Okay, so now theoretical formula to find out the natural frequency. So when we perform the experiment, we have to first find out the natural frequency. So I will note down this step. You draw the schematic diagram, and if you want the physical system, even you can draw this second diagram. So in the procedure, the first part is we have to find out the natural frequency of the system by using the formula omega n is equal to, it is square root k upon m. So k is the stiffness of the spring and m is the total mass including the mass of the motor. Okay, So here M, we can write M total. It is the total mass including mass of the motor. Then in the second step, run the motor at different speed starting from 0 rad per second to the maximum value. Then third step, for each frequency, that is each angular speed, note down the displacement of the mass. Then fourth step is plot displacement versus frequency graph. Okay, so this is the procedure to perform this experiment. Here first step is we have to find out the natural frequency by using this formula omega n is equal to square root k by m. Then for the experimental purpose, we have to run the motor at different RPMs or different speeds starting from 0 to some maximum value, and this maximum value, it must be greater than the resonant frequency. Then third step is for each speed we have to note down the corresponding displacement of the mass, and then we have to plot the displacement versus speed graph, and from this graph we have to find out what is the resonant speed. Okay, so up to this, is it clear to you what is the procedure and what is the setup diagram? So you note down these steps. So I won't provide any separate write-up. So whatever I will explain, you just note down this is a write-up. So if you have written this, then I will proceed. Okay, just give the reply. Okay. So first, we will try to find out the natural frequency by using theoretical formula. Okay. So you have already studied how to find out the natural frequency. Okay, so this is the schematic diagram. This is the mass, that is the mass of the platform. This is the motor. So motor, it has mass m. This eccentric mass, it is equal to m0. Okay. So for the natural frequency, we need to consider this complete setup as a rigid body, which is mounted on this spring and damper. Okay. So total mass, I will write here, mt is equal to mass of the platform plus mass of the motor plus eccentric mass m0. Okay. So given data is the mass of the platform, that is a capital M. This is equal to 5.16 kg. Then mass of the motor, it is equal to 0.81 kg, and the small mass m0, which is the eccentric mass, it is equal to 0.072 kg. Okay. So this is the given data. So total mass will be it is 6.042 kg. Then stiffness K, it is equal to this is 140 Newton per meter. So from this we will get the omega n is equal to, it is square root K upon total mass, that is mt, which is equal to, this is 140 divided by 6.042. So this value is 4.81. So it is 4.81 radian per second. Okay. Now from this omega n, we will find out the time period, which is called as a natural time period. T is equal to, which is equal to, so how to convert frequency in terms of time period? So we will have formula 2 pi divided by the omega n, that is T is equal to 2 pi upon omega n, which is equal to 1.31, 1.3 second. Okay. So why do we find out the time period? Because when we perform this experiment, then first value that will be available from this experiment, it is nothing but the time period. Okay. Frequency is not available directly by using the experiment. So time period we can measure by using stopwatch or by using some other mechanism. Okay. So this is the time period that is called as a natural time period, and this is the natural frequency. Now next part is the experimental part. So for the experiment, we have to note down the readings of the displacement and corresponding frequency. That means we will oscillate this mass. So this is the oscillation when this motor will run at some frequency, that is omega. Okay. So at different values of omega, this frequency, sorry, this amplitude or the displacement, it will change. So this is taken as a x. Okay. And x maximum value will be capital A, that is called as a amplitude. So we have to plot the graph of amplitude versus the frequency. So the observation table. So we perform this experiment by neglecting the damping effect. So this is the first observation table. By neglecting damping, that means zeta, it is equal to 0. Okay. Okay, this is your complete observation table. So we will first take the value as exciting frequency in terms of RPM. So this is the N. Then we will convert this RPM in terms of omega. So it will become an excitation frequency. It is 2 pi n by 60. Then we will measure the amplitude of the mass during the vibration. So this is the capital A. Then we will take frequency ratio omega upon omega n. So we have to divide this omega by the natural frequency. So we already have the value of natural frequency. And then we will find out the magnification factor. So you have studied magnification factor in the force vibration. Okay. So for the rotating unbalance, we have the magnification factor like this: A divided by m0e upon capital M. So A is the amplitude of the mass, m0 is the eccentric mass, E is the eccentricity, and M is the total mass of the system. Okay. So actually, the experiment that we are performing, it is the experiment of the rotating unbalance, because we will provide the excitation by using the motor and the eccentric mass connected to motor shaft. So the RPM that we will select, it depends on the natural frequency. So just observe here, our natural frequency is 4.81 radian per second. Okay, but during the experiment, we want the RPM so that we can rotate the system at the given RPM. Okay, so just convert this omega n in terms of RPM. So we will get some idea about the frequency range or the speed range. So RPM, which is corresponding to 4.81, it will become, so this is 60 into 4.81 divided by 2 pi. So this value is 54, sorry, 45.96. So this is the RPM. Okay. So this is the value of the speed at the resonant condition or at the natural frequency condition. That is 45.91. So we will select the range on the left side of this value and on the right side of the value. So we will get a complete graph of the displacement versus the frequency. So we will start from the zero value. So first reading is the 0 RPM. So omega will be 0. Okay. And at the 0 RPM, even this value will be 0. Then we will select the value 10. That is a 10 RPM. Then select 15 RPM. Okay. So continue this up to 70. Now just find out corresponding value of omega. Okay. So you can find out this by using this formula 2 pi n by 60 and just put this value here. So this value is 0. So omega will be 0. At 10, put the value and find out the omega. So this value omega is required when we plot the graph of amplitude versus frequency or magnification factor versus frequency ratio. So here omega for 10 RPM, it is 1.05. You find out remaining all the values. Okay. Now the value that we will get by using experiment, it is the A value. So if you vary the RPM or if you vary the omega, we will get the different value of A. So we have to find out for each RPM, that is 10, 15, 20, 25. Okay. So now we will perform the experiment. So first value that we will verify, take the n values in the sequential order from 0 to 70 and take the step size 5. So 0, 5, 10, 15, 20 in this order. Okay. Okay, so by performing experiment, we have to first verify this theoretical natural frequency, whether it is equal to the experimental natural frequency. Okay, so I have modeled a similar setup in the inventor software, and in the dynamic simulation, we will perform this experiment. So by using this experiment, we will give the initial displacement. So for this mass, we will provide a force in the downward direction. That means we will oscillate the system. Okay. and then we will remove the force immediately, and that will be the free oscillation. Okay, so for the free oscillation we will get a waveform. So frequency we can measure by using that waveform. We have to verify this frequency with this value, that is 45.991, or time period must be 1.3 second or near about 1.3 second. Okay, it may be 1.2, it may be 1.4. Okay, so just we will verify this, and then we will perform the actual force vibration experiment. So just tell me whether it is visible to you. So this is our physical setup. So this is not actually physical setup, it is the schematic diagram. So the screen is visible to you. So I will show actual setup for which we are performing this experiment. So basically this is a vibratory conveyor. Okay, so this is our experiment. I think I must have shown this during the force vibration. So this complete part, it is called as a vibrating screen. Okay, so generally such type of vibrating screen or vibratory conveyors, they are used for the material sorting. So generally these are used for the mining operation. So this complete part, it has some mass. So we have taken this mass as a capital M. So you can observe here. So this mass is nothing but the mass of the screen or mass of the vibratory platform. And this motor, it has some eccentric mass, and therefore it will provide a unbalanced centrifugal force. And because of that unbalanced centrifugal force, system will oscillate. Okay, and these oscillations because of the spring element present in the system. Okay, so as we change the RPM of this motor, the amplitude of this platform, it will change. So we have to find out the graph for that amplitude versus the frequency of the motor. So I hope this is clear to you what is the practical application or the physical setup. And for such physical setup, this is the schematic diagram. So now we will perform the experiment. So first part of the experiment is we have to find out the natural frequency by using the experiment. So this is our physical setup. So this is the motor which is connected to mass. This motor, it is having the eccentric mass. So this is the eccentric mass. For this mass, there is one center of gravity somewhere here. So just observe the center of gravity, then we will get the idea of eccentricity. Okay, so this is the center of gravity. So with respect to this point of rotation, the distance of center of gravity, it is 8.73. So you note down this value, 8.737. So this distance from this center point up to the center of gravity of this eccentric mass, it is 8.737. This is required to find out the magnification factor. Okay, now for this setup, I have connected two springs. So each spring will have the stiffness 70 Newton per meter. So overall the value is 140 Newton per meter because they are connected in the parallel. So just we have to add the spring or spring stiffness to find out the equivalent value. And we have taken the value of zeta is 0. So you can observe in the 3 dimension, this is our setup. I hope it is visible to you. So this is the physical setting. So for the free vibration, that is to find out the natural frequency, we need to provide some displacement, that is called as initial displacement, and then we will allow the system to oscillate freely, and for such oscillation we will measure the time period. So just observe, I will apply some force in the downward direction. So you can observe here displacement of this point, this corner point, in the downward direction initially, and then it will oscillate about the mean position. And then simultaneously we will observe the graph of the displacement versus time. So initially we are giving the displacement in the downward direction. So you can observe here black line in the downward direction. And once we remove the force, then system will oscillate. Now the force is removed. So system will start oscillating about this mean position. So is it visible to you, this oscillating system? Just give the reply. Okay. So actually I have taken the slow frame rate. That's why it is oscillating slowly. So I will change the frame rate so you can observe actual oscillations. So this is the free oscillation. So you can observe here, this is the displacement. So right now system is oscillating freely. This is not a force vibration. So the experiment that we have performed just now, this is the free vibration experiment to find out the natural frequency. Okay, because natural frequency we can only find out by using the free vibration experiment. So to find out the natural frequency, we need to observe this waveform. So basically this waveform is y-axis is the displacement and x-axis it is the time axis. Okay, so to find out the time period, we have to observe the distance along x-axis for the peak values. Okay, so I will select the first peak value. So here value is 3.26 second. Okay, so you can note down this value 3.26. So here t1 time it is equal to 3.26. So in the write up, so the first part, omega n calculation by experiment. Okay, so the waveform that we have obtained is like this. This is x versus time. So this is the simple harmonic waveform. So you can take this value as a t1. The second value is a t2. So you draw this waveform, mention here omega n calculation by using experiment, and t1 value it is equal to 3.26, and t2 value this is 4.48, or we can take 4.49. So time period it is equal to t2 minus t1. So this is equal to it is 1.23 second. Okay, and from this we will find out our natural frequency. So omega n experimental it is equal to 2 pi upon t experimental. So this value is equal to this is 5.1. Okay, so we have to check this value with the theoretical value. So what is our theoretical value? We have already calculated by using formula omega n is equal to square root k by m. So theoretical value is omega n is 4.81, or time period is 1.3 second. Okay, so it is near about theoretical value. So this value omega n, if we compare this value with the theoretical value, it is equal to 4.81, and time period, so t theoretical, this is equal to 1.3 second. So it is near about the theoretical value. Okay, so you note down this. Now the next part is we have to perform this experiment. So we have to run the motor at various speed starting from 0. Then slowly we will increase the RPM 10, 15 RPM, 20 RPM, 25 RPM. Okay. And then for corresponding RPM, we will find out the amplitude. That is the capital A value. So in the free vibration, this is called as amplitude. Okay. And amplitude remains constant for the free vibration. That is why it is called as a simple harmonic motion. Okay. So up to this, is it clear to you?
आता ऍप कसं काय करून इन्स्टॉल करू आता नाही आता नंतर बघ
Siddesh Sawan, mute your mic.
तेच फ्री जाऊ फक्त तेच काय करून करू चार पण
Okay, so up to this step, is there any doubt how to find out the frequency by using experiment? Okay, so now we will start with the experiment. So slowly we will rotate this shaft or the eccentric mass by the given RPM 0, 10, 15, 20. So actually this graph is, it is time axis and this is the RPM, but this RPM is converted in terms of the velocity degree per second. Okay, so when we take the 10 RPM revolutions per minute in terms of degrees per second, it will become 60. So first we will select the 10 RPM, that means 60 degrees per second. Okay, and for this RPM we will find out the displacement. So just observe. So you can see the rotation. But it is quite difficult to observe the displacement of this mass because at low speed displacement will be very small. Okay, so by using graph we will find out that displacement. So here you can see the displacement. So this is the displacement. Just wait for a minute. Okay, so this is the maximum value of the displacement. So we have to just observe this maximum value. So here you can see it is a 0.006. So this is in mm. So 6 into 10 raised to power minus 3 mm. So this is the maximum value. So if you observe this diagram, so this value is very small. Okay, so actually it is not visible in the diagram. So if you change the speed gradually, then the RPM will, sorry, displacement will increase. Okay, so first value for 10 RPM, you note down this value. This is 6 mm, sorry, 0.006 mm. Now I will increase the speed. Just I will shift the speed directly. So I will give the in between readings. Now just consider the RPM 35. So for 35 RPM, degrees per second will be 210. Now just observe the value of the displacement. Okay, so from this graph, we will get the maximum value. So this value is 0.214. Okay, you note down the value at 35 RPM. If you further increase the value, and suppose the value of RPM is equal to the natural frequency. So the natural frequency corresponding RPM is 48. So at this value, so it is value is 45.91. Okay, so if the value is near about this 45.91, so just we will take the 50 value directly. So just observe the waveform. So if I adjust the speed at 50 rpm, so 50 rpm is corresponding to 300 degrees per second. So you can observe the value of the displacement. So right now motor is running at the rpm 50. So this 50 rpm is near about the natural frequency, that is equal to 46. Okay, so you can observe at the natural frequency or near about natural frequency, we will get the maximum value of the displacement. Okay, so this is 4.94. So this is near about 5 mm. Okay, and suppose if you cross this natural frequency value, and suppose I take the value at 70 rpm. So you note down this, for 50 rpm, the value of the displacement is 5 mm. And suppose if I cross this frequency, and if I take the frequency, it is equal to 65 rpm. Okay, so just we will check what is the change in the displacement. So I will select the rpm 65. So 65 rpm is nothing but the 390 degrees per second. Now just we will observe the displacement change. So here you can observe the displacement change. The displacement is suddenly dropped to point something 6 mm. Okay, and previously we had the displacement as a 5 mm. So here you can see the displacement or maximum value of the displacement. It is 0.61 mm. So this is at the speed 65 rpm. Okay. So from this experiment, you must have observed, if you take the very low frequency or low rpm, displacement is very small. If you increase the value of the displacement, sorry, rpm, so at low rpm, for example, n is equal to 10, our value of displacement or amplitude a is equal to, it is near about 0.006 mm. Okay. Then if you step by step increase the value, your amplitude will increase. Suppose we reach to the natural frequency region, that is called as a resonance condition, where omega it is equal to omega n. So for this omega, our rpm n, it is near about 50. Okay, so at this 50, we have got the a value as a 5 mm. So you can check here drastic change from 0.006 to 5 mm. And then if you further increase the rpm, let us take rpm, it is equal to 65. Okay, so again you can observe the change, a becomes suddenly 0.6, okay, mm. So So again here, displacement or the amplitude is decreasing with increase in the RPM. So by using these different values of RPM or operating speed, we can study the response of the system. Okay. So to study the response, we have to plot the graph. So that graph will be y-axis will be amplitude. Our x-axis, it will be the external frequency, that is omega. Okay. So we have to observe this graph. So for that, we will need a set of the reading for different values of the operating speed. So I will give the direct reading, just you note down. So first value is 10. We have got the value of A is 0.006. Then for 15, so you can convert these values. So I will skip the table for the omega. And you write down this. For 15, the value of A, it is equal to 0.014. Then for 20, value is 0.026. For 25, this is 0.117. Then 30, this is 0.186. For 35, this is 0.413. Sorry, for 35, the value is something point. Yes, what is the value for 35? It is 0.2 something. This is 0.214. So this is 214. Then for 40, it is 0.414. For 45, value is 1.242. Then for 50, value is 5 mm. For 55, this is 1.18. So actually this region, this is called as a natural frequency region, or we can call this as a resonance. So when we design any vibratory system, then we should avoid this region. Otherwise, there is chance of failure of the system due to excessive oscillations. Now again at 55, we have the value 1.18. So this is at 55. This is at 50. Okay. Then at 60, we have the value 0.76. And there is one extra reading, 65. The value is 0.61. So these are the set of reading for the amplitude. You find out the values of omega, 2 pi n by 60. Okay. So now we have to plot graph of the amplitude versus the frequency. So during the force vibration, we have studied different graphs. Okay, just we will refer that graph, so you will get the idea. So this is the graph for simple force vibration. Okay, so here magnification factor was the y-axis and x-axis is the frequency ratio. We have got the similar graph for the rotating unbalance. So this is our experiment. So this is the motor and this is the mass, and there is one eccentric mass which is connected at radius E. So you can see here figure. Okay, so for the oscillation of this mass, we will observe this type of graph. Here you can see we get the peak value at the frequency near about the resonant condition. So one means what? This is called as a frequency ratio, x-axis. That is nothing but the omega upon the omega n. So omega in the numerator is nothing but the frequency of the excitation. Omega n is the natural frequency. So when this ratio becomes 1, that means there is a resonant condition, and suddenly there is a rise in the amplitude or the displacement. Okay, so we have to check by using our experiment whether we get the peak value at the resonant condition. Okay, so right now this graph is magnification factor versus the frequency ratio. We will first draw the graph of the amplitude versus the frequency ratio versus frequency only, and then we will find out the graph of frequency ratio. Okay, so have you written this complete table? Just find out these values of omega. Okay, now on the graph paper, you will need one graph paper. So I will explain the procedure. So you can draw the graph afterwards. So it is a graph of amplitude A versus frequency, that is the omega. So you will have the values of A and omega. So initially omega is 0, then gradually increase the omega, and A value will be 0 when omega is 0. So it will increase. So first value you have got is 0.006, then this is 0.014, then 0.026, 0.117, 0.186, so on. So by observing maximum value and minimum value, you select the proper scale, 1 centimeter is equal to, and then plot the graph. So y-axis, it is the amplitude, x-axis, it is the frequency. Okay, so your graph, it will start from this value 0 0. It will increase gradually. Do not draw this graph in the write-up. I'm just explaining. Then at the peak value, after that it will decrease. And again it will approach to the 0 value. So you will get the nature like this. Okay, so this is for amplitude versus the frequency. The second graph that we have to draw, it is the graph of magnification factor versus frequency ratio, omega upon omega n. So for that we have to find out the magnification factor. Okay, so what is magnification factor for the rotating unbalance? So for the rotating unbalance, magnification factor, it is nothing but the amplitude divided by m0e upon the m. Okay, and this ratio is equal to r square divided by square root 1 minus r square bracket square plus 2 zeta r bracket square. So this is for the theoretical formula. Okay, we have to just plot the graph of a upon m0e upon m versus frequency ratio r. Okay, so a upon m0e upon m we will get by using our experiment, because a is variable. These values are constant. M0 constant, E is constant, and M is constant. Okay, so just you have to prepare one table. So this is for the second graph. This is your A value, and the second value it will be A upon M0E upon M, and then last value will be frequency ratio R, omega divided by omega n. Okay, so there are various values of a upon m0e. So just find out this value m0e upon m. So m0 is mass of the unbalance. Okay, so that rotating unbalance has a mass. It is 0.072. E value, that is eccentricity, it is 8.73 mm. So it is 10 raised to minus 3 divided by m is the mass of the total mass of the system. So that total mass is 5.16 plus 0.81 plus 0.072. Okay, so find out this value. So this is equal to 1.04 10 raised to minus 4. Okay, so just check the answer. So m0 is 0.072 kg. Okay, so m0e upon m. From this, find out the magnification factor. So this complete value for each reading of a, and then you have to plot the graph. So this is your second graph. This is m0e upon m. This is a divided by. This is called as a magnification factor versus frequency ratio omega upon omega n. Okay, so the graph will start from 0. Then we will have one value, 2, 3, 4. Similarly, this is 1, 2. So here you can observe when frequency ratio is 0, a value will be 0, or this magnification factor, it will be 0. So graph will start from this value. Okay, then it will increase gradually. It will go to the maximum value, and then it will decrease. And when the frequency will become very high, graph will run parallel to the 1 value. Okay. So we will observe a similar graph. So I will show the output. So here you can see the first graph, it is RPM. So x-axis, it is the RPM. So this is 10, 15, 20, up to 70. Okay. This is the A value only. So you can see here. So I have taken exactly the resonant condition at 48. This is the additional value. So at 48, the value that we have got is a 5.92 mm for the displacement. Okay. So y-axis, it is the amplitude. So this is the capital A. And x-axis, it is the RPM, that is a capital N only. So you can see here, it will start from 0 value, and suddenly at the resonant condition, we will get the maximum value. Anurag Bhogle, do you have any doubt? You can use that annotation option if you have any doubt. Yes, Anurag Bhogle. Okay. So this is your first graph. So actually we have to plot the graph of amplitude versus frequency. Okay. So you can see here. So this is our RPM. Shubham Sawan, mute your mic. Okay, your first column, it is the RPM N. Then the second column, this is the angular speed, that is the frequency omega. Okay, so for 10, frequency is 1.04. Now this is the frequency ratio, omega upon omega n. So this is omega upon omega n, that is the frequency ratio. And this is the amplitude. So this is capital A. You can note down all the readings in the observation table. And the last column, I think I have made the mistake in the calculation of the M0E upon M. Just check that calculation once again. So actually we need the graph A upon m0e upon m. So this value, m0 value, that is the eccentric mass, which is equal to 0.072 kg. E value, it is 8.737 10 to the power minus 3 meter. Your m value, m is the total mass. So here mass is 5.16 plus 0.81, that is the mass of the motor, and that eccentric mass m0. So this is 0.072 kg. So find out this denominator. So that is equal to, this is 1.041 10 to the power minus 4. Okay, so you will get these values as a upon m0e. So this value is nothing but a divided by, this is m0 you can take this screenshot and then you can prepare the observation table. You have to just put these values as it is in the observation table. So you have to plot the graph of omega, that is this table, versus amplitude. Okay, and second graph is this table versus frequency ratio. Okay, so is it clear to you how to plot the graph? So if there is any doubt, you can ask. So actually this graph, it is of the frequency ratio. So x-axis, it is the frequency ratio, and y-axis, it is the magnification factor. Okay, so this value. So actually we have just taken the reading up to 70 RPM. So we have to further increase the RPM in order to get the higher frequency ratio. So anyhow, we have reached up to the frequency ratio 0.5. So we have to add more values so that we can observe here. Actually, our standard graph for the rotating unbalance, it becomes flat at the magnification factor 1 for the higher frequency ratio. So you can observe here. So this is the graph. So when zeta is very small or negligible, you can see there is a peak value at the resonant condition. And then if you further increase the frequency ratio, that is a higher frequency ratio, then you can observe the graph will become flat when the magnification factor is unity, that is a 1. Okay, so for that we have to select some higher frequency ratios, 1.5 or 2. And in order to get this higher frequency ratio in our calculation, we need to find out the values of RPM exceeding 70. So we have to take 75, then 80, okay, and then corresponding we have to find out the A value. Then somewhere we can observe the flat graph when magnification factor is 1. If you want, you can take the screenshot of this graph, and you can take the screenshot of these readings. So you have to write this reading in the write-up. So there are two observation tables separately. The first is A versus omega, and second is A upon M0 E up versus frequency ratio. That is magnification factor versus frequency ratio. So this is magnification factor, and this is your frequency ratio. So you will get similar graph, but actually right now it is not visible exactly. Okay. And this graph is just for RPM versus amplitude. So you can take this screenshot for this experimental setup. So when you prepare the write-up, you add these diagrams. You draw one schematic diagram on your page, and also in the PDF you can add this diagram directly. Okay, so you can add this diagram, then you can add the graph. So you take the screenshot. So at this point it is called as a peak frequency, and which is near about the natural frequency. Okay, so you complete this experiment. Just give your attendance. So we will stop here.